Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So basically this is a lecture video for subject Electrical Circuits 1, code BEB10303. And in this video we are going to continue our discussion for chapter 4, which is circuit theorems. Okay, so what are the topics that we are going to cover in this video? Based on the contents of chapter 4, which is 4.3, Thevenin's and Norton's theorem. But in this video, we are going to cover only on Thevenin's theorem. Okay. And for the Norton's theorem, we are going to cover it in the next following video. Alright. So what is the Thevenin's theorem actually? And then why do we need the Thevenin's theorem? So basically, let's say you have a linear two-terminal circuit. Okay. And then you connect your circuit to the load. Okay, so usually we can consider that the elements in the linear two-terminal circuit is a fixed element. Okay, and then you connect it to the variable load. So, for example, let's consider the linear two-terminal circuit is your electrical wiring system inside your house. Okay, so the terminal represent the household outlet terminal. Okay, so the household outlet terminal may be connected to the different appliance constituting a variable load. Okay, so each time the variable element is changed, the entire circuit has to be analyzed all over again. So to avoid this problem, the Thevenin's theorem provides a technique where you can represent the fixed part of your circuit, which is this part, to the equivalent circuit. Okay, so once you represent the whole complicated circuit into here, you can just analyze your circuit whenever your variable load is changed. Okay, so according to the Thevenin's theorem, the linear two-terminal circuit can be replaced into this. Okay, where you have a voltage supply, we call as a V Thevenin, connected in series with the R Thevenin. Okay, so this is your variable load. So now let's have a look at the definition of the Thevenin's theorem. So Thevenin's theorem states that any linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH connected in series with a resistor RTH. Okay, so this is the definition of the Thevenin's theorem, where your VTH is the open circuit voltage at the terminals. Okay, and then the RTH is actually the equivalent resistance at the terminal when the independent source are turned off. Okay, so how to find the V Thevenin and the value of the R Thevenin actually? Okay, so first of all, you just remove your load. Okay, and then you find what are the voltage open circuit here. So the voltage open circuit is represent your V Thevenin. And then with your variable load is removed, you just turn off all the independent source and then you set it equal to 0. Okay, so in this case, meaning that the current source, you make it open circuit, and for the voltage source, you make it to become short circuit. Okay, so the R equivalent will be equal to the R Thevenin. Okay, so let's have a look at the step-by-steps in the process of finding the V Thevenin and then the R Thevenin. So first, you need to remove the resistive load. Sorry, you need to remove the variable load, RL. Okay, and then after that, you find the R Thevenin from the terminal AB. We turn off all independent source. Okay, remember, you need to turn off all your source, include your voltage source and the current source, and then you just find the R equivalent. So the R equivalent will be represent your RTH. Okay, and then you put back your independent source to turn on back, and then you just find the V Thevenin from the terminal AB. So the V Thevenin is actually the V open circuit at the terminal AB. Okay, and then you can just draw the Thevenin's equivalent circuit. Okay, so let's have a look at the following example on how to find the Thevenin's equivalent circuit. Okay, based on example 4.5, you are given this kind of circuit. Okay, so from here you can assume this is your linear two-terminal circuit. Okay, so this is your linear two-terminal circuit. Exclude this one. Okay, and then you have a terminal A and B connected to the variable RL. Okay, so this is your load. Alright, so now we are going to replace this whole thing with the equivalent Thevenin circuit. So how to do that? So the step by step is, first of all, you need to remove the RL. So here I just remove the RL first. And then after that, we turn off all the independent source in order to find the value of RTH. Okay, so here your just now you have a voltage supply here, so you turn off voltage supply, meaning that V equal to 0, so you just short circuit it. And then here just now you have a current source, you turn it off, meaning that the current is now become open circuit. Okay, right, so based on this circuit, you just need to find your R equivalent. Okay, so your R equivalent based on this, from this terminal, is equal to your R Thevenin. Okay, so in this case, your R Thevenin will be a combination of series resistor. So you have 4 plus 6 and plus 2. So your R Thevenin will be equal to 12 ohm. Okay, next, you need to find your V Thevenin from the terminal AB. Alright, so you just put your source back to its place and then you remove your RL. Okay, so now here is your V Thevenin. Okay, so V Thevenin is actually the V open circuit at the terminal AB. Alright, so based on this, you can apply the KVL in order to find the V Thevenin. So you can assume here you have a mesh current I. Okay, here you don't have any mesh current because here it becomes open circuit, right? Okay. So in this case, your I going down and you have another current source going out, which is 5 ampere. So here you have I is equal to negative 5 ampere. Okay, and then after that, we can just apply the KVL around the loop. So before you can apply the KVL, you need to apply the polarity of each of the terminal based on the mesh current I first. So here you have positive, negative, and negative. Okay, and then here is your V Thevenin. So voltage here will be equal to the voltage here. Okay, even though you have the resistor here, but no current flow through here, so no current drop through the 2 ohm. So that's why the voltage here is same as per here. So here also your V Thevenin. Okay, where you have a positive, negative, V Thevenin. Alright, and then after that, you can just apply the KVL. From this point, you have a positive terminal. So plus 4I minus, because here is minus 20 plus 6I, okay, plus V Thevenin equal to 0. Alright, and then after that, I can further simplify my equation. So V Thevenin will be equal to 4 plus 6 is 10. So we bring to this side, so we get negative 10I plus 20. Okay, and then we just substitute the value of I is negative 5. So negative 10 multiplied with negative 5 is 50. 50 plus 20 is 70 volt. Alright, so this is the value of the V Thevenin. And then finally, you can draw the Thevenin's equivalent circuit, where you have the V Thevenin 70 volt connected in series with the R Thevenin, which is 12 ohm. Okay, so this is your terminal AB. Okay, and then you can just draw your RL here. So this is your RL. Okay, right. So basically, in summary, you can actually represent this circuit to this. Okay. Okay, now let's have a look at one more example. Based on the following circuit, you need to find the Thevenin equivalent circuit at the terminal AB. And then you need to calculate the current and voltage at resistor 3 ohm. So meaning that you need to find the current that flow through your R load. Okay, so let's do it one by one. Okay, so step number 1. First, you need to remove your RL. Okay, and then you just turn off your independent source. So in this case, just now you have a voltage source here. So when your voltage source is off, meaning that your V is 0. So V is 0 is your short circuit condition. Okay, so that's why we short it here. Alright, and then we need to find the R equivalent from the terminal AB. Okay, so here your R equivalent will be equal to your R Thevenin. Okay, so in this case, what you have a combination of parallel and series circuit. So 5 and 4, 5 ohm and the 4 ohm is connected in parallel, and then connected in series with 1 ohm. So here you have 5 multiplied with 4 divided by 5 plus 4 plus 1. Okay, so your R Thevenin will be equal to 3.22 ohm. And And then next, you need to find your Thevenin. So Thevenin is considered as your V open circuit at the terminal AB. Okay, you just put back your source. Okay, so here is your VAB is equal to your Thevenin. Okay, and then the voltage across here will be equal to the voltage across here. So here you have Thevenin. Okay, as you can see from here, you have a 1 ohm, but since here is an open circuit, so no current will be flow through the 1 ohm. So that's why the voltage here will be equal to the voltage across here. Okay, so here is Thevenin, here also Thevenin. Alright, and then you can just apply your KVL around the loop. So in order to do that, we apply the mesh current to the first loop. So here we consider as a I. And then based on the mesh current, we assign a polarity for each of the elements. So here you have positive, negative, and here is positive, negative. Okay, so here is negative, positive. Okay, and then after that, we can apply the KVL. So from this point, you have a negative sign. So negative 28 plus voltage across 5 ohm is equal to 5I. Okay, and then plus 4I. Okay. So based on this, you can further simplify your equation in order to get the value of I. So you have 5 plus 4 is 9. So I will be equal to 28 divided by 9. So I will be equal to 3.11 ampere. And then now you need to find the value of Thevenin. So Thevenin, voltage across here, is equal to the 4 multiplied with I. You just apply the Ohm's law. Okay, so Thevenin will be equal to 4I. I is 3.11, so 4 multiplied with 3.11 will be equal to 12.44 volt. Alright? And then, next you just draw your Thevenin equivalent circuit. So this is your Thevenin equivalent circuit where you have a V supply is the Thevenin. Okay, so you have the R Thevenin here and then connected to the terminal AB. And then you just put back your resistive load here, which is 3 ohm. And then based on the equation asks you to find what is the value of current and then the value of the voltage that go to the resistive load. Okay, so you can just apply your Ohm's law in order to find the I. Okay, because the question asking you find the current that going through the resistive load. So I will be equal to V divided by R. So in this case, V is 12.44 and R will be equal to the R total of the whole circuit. So here and here, it is connected in series, so you just add on the number. Okay, 3.22 plus 3. And then finally, I will be equal to 2 ampere. Then after that, you need to find what is the voltage across the resistive load. Okay, so you can just use the voltage divider rule. Okay, voltage divider rule. So in order to find the V voltage at the 3 ohms, so you just use the formula. You have 3 divided by 3 plus 3.22 multiplied with the voltage source, which is 12.44. And then finally, you have the voltage across the 3 ohm will be equal to 6 volt. Alright. And then that's all for now. Thank you for watching my video. And thank you for your time. I'll see you in my next video. Okay. Bye.